Welcome back to this afternoon session. I'm happy that we have Erinn with us for this talk. She's from the University of Waterloo in a group called CRISP. It's one of the largest research groups in security in Canada. And she will talk about distributing data or keys or things that you need for encryption across multiple devices.
Okay, is this good? Cool. I just want to apologize in advance. I cannot sleep on planes, so if I stop and just start blinking a little bit, I'm sorry. I apologize in advance. So I know this talk says cryptography in the title. I just want to reassure you there's almost no math in this talk. I have some less than signs. I think there's a plus sign maybe in there in a place or two, but that's not really what I'm interested in. Threshold cryptography dates back to, I think, around 1980, so it's not a new idea. What's new is using it specifically for just a single person that has a bunch of devices, and I'll talk about more on what I mean in a second. So I'm going to spend a lot of time just talking about the threat model of threshold cryptography in this personal device setting, although I will talk about some implementation stuff towards the end. But what I'm really interested here is is the threat model. So I think it's a fair assumption that almost everyone in this room has at least two devices capable of computation. So you have like a computer at home, laptop, desktop, whatever it might be, and then you have a smartphone as well. Maybe you have a tablet, maybe your sneakers are internet connected, maybe your scale is internet connected, your refrigerator. Just the other day, I saw a news release about internet-connected condoms, so chances are you've got more than one thing that can do something computational. This is super convenient. I actually brought a massive laptop with me, but normally I could just bring a tablet with me when I travel, but when I'm at home, I've got a desktop, 6 monitors, 8 cores processor, whatever. Super convenient, but when you start trying to use end-to-end encryption or strong cryptography in general, that convenience turns on its head when you start using multiple devices. The root of this problem is that you have a private identity key. So it's just basically a file. You have to keep it secret, and you need access to that same identity key from all of your devices. So we run into problems like how do we transfer it between the devices securely? I know a lot of people that use secure email will actually email their private keys to themselves to copy it to another device. Think about what you've done there. And of course, there's also with every new device that you add, every new device you get, there's an increasing chance that you're just going to set one down somewhere and it's going to get stolen. And so theft resistance is really the focus of my talk. All right, so just to give you the basics, let's suppose we've got some device and we've got some key. Details don't matter, but this key represents our identity. We can use it to, if we have access to this private key, we can use it to authenticate ourselves. We can use it to encrypt things like this. So in this example, I'm going to say that this is a signature key, and so I can just use it to produce a signature saying, hey, this data really came from me. So we want to be able to use this one key on all of our devices. The easiest solution is just take it, copy-paste it to all other devices somehow. A lot of people, like I say, do this manually, USB keys, whatever. There are some clients like Whiteout that will do it for you, usually encrypting it with a strong passphrase and transferring it in software, so you can make it kind of nice. But there are still some huge problems with this. The biggest one is that if you lose one of your devices, and especially if it gets stolen, that's the same key on all your devices, and so it's kind of like all of your devices have been compromised, even though you've just lost one. So, for example, you have to tell everyone that you ever talk to, hey, this key has been stolen, don't use it for me anymore. You have to generate a whole new key. You've got to do this whole synchronization process again, get it to all your devices. Your new key, you've got to tell it to everyone, hey, in addition to not trusting this old one, use this new one. And some of you have done this out-of-band verification thing where you like get together and you compare numbers or QR codes. If you've done that with every single person you talk to, and then you lose one device, you've got to do that with everyone all over again. Another frequent solution is to just generate a different key, completely unique for every one of your devices. And there are a few programs out there that do this. This is what Apple iMessage does, for example. And so the nice thing here is that if we lose one device, we just have to tell people, hey, I lost the cyan key. I don't have it anymore. Stop trusting it. Then we still have all of our other keys as well. But of course, the attacker, when they get the device, before you notice, they still have access to a usable key. Like they steal your smartwatch, they've got your cyan key. Until you notice that and start telling people you've revoked it, they can still use it and impersonate you. There's also an interesting privacy problem here, where if you have a different key for each device, there's a privacy problem where people that you're communicating with can see which device you're on right now. So for example, if your boss is out of town and you're at home and you want to say, hey, the office is great today, the climate's a little off, and they see that you're sending that from your home computer, the boss knows you didn't come to work today. So this is an academic work. It comes with a paper. So you can go look up details and stuff. And we actually looked at as many solutions to this problem as I could possibly think of. So if you're interested in more solutions, like there are ways that you can make this nicer using subkeys and things like that. So you can go have a look at the paper if you want to see a bunch of solutions and the problems we found with them. So we're going to skip right to the fun one for this, which is threshold cryptography. So the idea here is that we take whatever the private material is, private key, some secret, whatever, and we split it into shares. And then so however many devices you have, for example, we have 4 here. So we would split the private key into 4 shares, hand one to each device. So this slide is a little bit misleading. It looks like we just take, say, a 512-bit key and split it up into a bunch of 128-bit parts. That's not actually what we're doing. So we want it to be the case that if we have a 512-bit security level originally, splitting things up into shares like this doesn't mean we're dropping to, say, 128-bit security on each, or 384-bit security. Sorry, that was a little bit of math. Yeah, so the important thing here is that if an attacker steals just one device, they don't learn even a fraction of your private key. And so the way this works is that we pick a threshold. So let's say, for example, this user has 4 devices, and they decide that, hey, 2 devices need to work together in order to do some operation using the private key. So in that case, they can pick any subset of their threshold number of devices. They can set it to whatever. They could set it to 4 if they want and say all 4 of these devices need to be working together. Or they could set it to 2 and say any combination of 2 devices can work together. These devices working together doesn't mean they need to be physically next to each other. As long as they're in communication somehow, or it's Bluetooth, over the internet, it's up to the user. As long as they can communicate with each other, they can work together to do some operation. If you've worked on threshold cryptography before, you might have heard of Shamir secret sharing, which is kind of the oldest threshold cryptography trick we have. It's really cool. It allows you to just take any arbitrary secret and split it into shares and hand one to each person. And so in the scenario with t equals 2, in the scenario with t equals 2, we get any 2 devices working together. We could regenerate the secret value, which in this case is our signing key, and then we can use that signing key to produce a signature. It could be an encryption key, and then we can use it to encrypt things, whatever. This is great, but we can do one step better using more recent advances in threshold cryptography. And that is, instead of regenerating the private key and then using it to do some operation and get some result, We can actually use more complicated threshold cryptography schemes. In this case, what's called a threshold signature scheme, in order to jump straight to the result. So if, say, all of your devices are compromised by, say, malware, and this malware is constantly listing out the contents of memory and sending them to the attacker, at no point is your private key held in memory, and so the attacker never actually gets a copy of it because that copy is never regenerated. Okay, so some of the stuff that we did, we created this piece of software called Shatter. Consists of two things: a library to make doing this stuff easier, and also a set of applications just kind of showing you how it works, as well as management applications that let you say, hey, set it up with these devices, add a new one, revoke one, etc. I just want to give a quick caveat emptor. I'll give you a link to this software at the end of the talk, but it is what I call gradware. I'm a grad student. I haven't programmed. I don't do application security. It's not my area. It's a proof of concept. I want to see how the performance works. I want to see the usability, things like that. Please don't put it on your phones and use it to protect your nudes or whatever. Just some definitions. We're going to have n devices. That's the total number of devices you own. And then the user is going to pick some threshold t so that t devices need to work together. The bounds on t, of course, you can't have more than the number of devices that you have, because you don't have that many. And you could actually set t equals 1, so you only need one device working with itself to do threshold crypto. But then you're doing a whole lot of expensive operations for no reason. So we want it to be the case in any shatter algorithm that we never regenerate the private key in memory. And we want it to be the case that if the attacker steals less than t devices, they get no information whatsoever about the private key or the private information. They don't get 128 bits worth of it or anything. No information at all. So just to give a quick example of n and t again, let's suppose in this case that n is equal to 4 again, and we're going to play with t equals 2 here. So any two devices need to work together. So suppose that in this scenario we lose one device, the attacker gets it, the attacker learns nothing about your private key. In this case, what we would do in the event of losing a device is we would go get any combination of two of our remaining devices, and we would revoke the one that we lost. So revoking access to devices as part of your group of devices is also a threshold operation. So is adding new devices. Suppose the attacker manages to steal two of our devices, then that means that, in fact, they can use these two devices. They have the threshold number. They can do anything they want with the key. They can, use it to decrypt our data if that's what we were using it for. They can sign things as if they were us, etc. We still have two devices, however, so we can go and revoke those original devices with it. However, the attacker still has our key, though, so not that great. The nice thing, however, though, too, is that, say we were using it to encrypt our data, since we still have two devices left, we can also, we haven't lost access to our data. Unlike in the case when an attacker steals 3 devices. In this case, the attacker gets access to all our stuff, they can impersonate us, and we don't have the threshold number of devices left. We only have one device left, we need 2. So in this case, you lose, if you're using it for email encryption, you will lose access to all the data that you were using that key for. Of course, this is still better than just using one device and the attacker getting your one device. So to talk about some of the goals for a solution, and when we compare and contrast this to other schemes like syncing all your keys, this really highlights where the difference comes in. So one of our goals, and this is really the most difficult one actually, is to get backwards compatibility. So Shatter, that I'm talking about, our software, is not a new messaging application. I want to be able to use it with an existing end-to-end encrypted application. So for example, if you use WhatsApp on your phone, that's end-to-end encrypted now. And so I want to be able to talk to you and have it so that you're using the original WhatsApp, I'm using a Shatter-compatible WhatsApp, an app that's been modified to use threshold crypto, and the people I'm talking to don't even have to know that that exists. And so in order to do that, we need to be able to create threshold versions of the crypto systems that these apps are already using. And so that's really where the big challenge comes in, is some of the encryption algorithms and the signing algorithms are sometimes quite hard to convert to threshold versions of themselves. We want device anonymity, where using your desktop looks the same as your smartphone, looks the same as your smartwatch. We don't want the people you're talking to be able to see what device you're on. Interestingly, iMessage doesn't have this property. If you know what you're doing, you can go in and look at the iMessage protocol, and it'll just send you a list of anyone's devices with like the device name and everything. So we want each device to be anonymous. So our solution, Shatter, has both these properties. Theft resistance, like I say, is one of our huge goals. This is a very wordy slide, I'm sorry, but I just broke it down into weak and strong theft resistance. And so the idea here is that when you have one device and you send a request to another one of your devices saying, hey, let's sign something, let's decrypt something, whatever, you have an implementation choice there where does the device say, yeah, sure, automatically, I'll do it, or do you have like a notification pop up and the user has to click yes on it? It's just an implementation decision as to whether it does it automatically or not. And so weak theft resistance is this idea that if you have a whole bunch of devices and they all automatically participate in requests, can an attacker recover your private key? And so in the Shamir secret sharing scheme, the private key gets regenerated in memory, which means if an attacker can send out a request and get it accepted automatically, then they can also use it to just regenerate the private key. That's the result of that operation. Strong theft resistance is where even if people are saying yes automatically, so the attacker only steals one device, they still don't learn your private key. Even if they can say, they can get an output of like a signature or they can decrypt something, but they don't get your private key, so they can't do that again in the future once you've revoked their device that they've stolen. So again, Shatter has strong theft resistance. And the final set of properties, we want to have only one public key representing the user. We don't want the people we're communicating with to see a whole bunch of keys for your devices or to constantly be saying, hey, I've got another key, whatever. We want the user's identity to just look like a single device. We don't want any concept of a master device or certificate authority. A lot of schemes, you can do this with PGP where you have a single master key and you can use that to issue sub-keys for your other devices. But then if your device with the master key gets stolen, then the attacker can use that to do a lot more damage than they could with a sub-key. So we want each device to kind of look the same so that no particular one is more vulnerable than another. So Shatter has both those first two properties. We fall down a little bit on this third property, which is obviously ideally if you're sending an email, you don't want to have all these devices turned on and connected to each other. So that's a property that you want, right? Like you want to be able to send a secure email from your smartphone even though all your other devices are turned off. And so we do fail on that. We need the devices to be on and connected to each other. However, there is a little bit of a trick that we can use, assuming that your device is internet connected. I'm a PhD student. I don't know if we mentioned that, but the entire subject of my thesis is mostly around these edge cases where a user only has one device or things like that. There's some really interesting edge cases that come up. So this is one of them, when a user only has one device, which means they can't use our system. However, as long as they're doing something like sending secure email, they need to be connected to the internet anyway. And so they could use, for example, Amazon EC2 to act as if it was one of their devices. So you just install the Shatter client on it, and then you have it so that whenever it gets a request from your one device, automatically says, yes, okay, I'll participate in this. You have to worry about Amazon themselves going into your machine and spoofing requests and having your phone participate in them. And there's a really easy implementation solution to that. which is just don't accept requests from cloud devices. And so in the case that you lose your phone or someone steals it, you would then go log into your Amazon Cloud account, revoke it. Of course, you still want to have access to your key to like decrypt data or continue, get a new device and replace your same key on it. And so you can also treat a piece of paper as if it were a device. You issue a share to, like a backup share to a piece of paper, and then you just print it off. You put it somewhere secure, safe deposit box, under your mattress, whatever. And then if you lose your device, you log into Amazon, you scan in your backup share, and then you can use the two things together to regenerate your key and keep using it as if you've never lost the device. So just going back to our implementation, I'm going to go through this a little bit quickly. But like I said before, Shatter is a library which, so if you, for example, are the developer of WhatsApp, is the developer of WhatsApp here? I doubt it. Okay. There's some people that developed applications that I know are here, so. Yeah, so say, for example, you're the developer of WhatsApp. You take our library, you drag and drop it, and then it just starts replacing all your crypto with our threshold versions of it. Not quite on Android. You have to add some stuff to the manifest file, but very, very easy. WhatsApp is not part of our suite of applications, but what we do have is these Shatter clients, where you just have one client on each of your device, and then if you have like WhatsApp, Facebook Messenger, an encrypted file application, they can all communicate with these Shatter clients installed on the device. So you only need to set up that group once, and it manages all the threshold-enabled applications from it. Currently, our Shatter clients run on Windows OS X Linux. It's just written in Java, so anything that will run Java, it'll run on. We have an Android version of it. Android took a little bit of work, and an Android Wear client as well. So I have actually gotten this running on a smartwatch. So that's what the library is for. And then, that's what the clients are for. And then the library itself is the thing you drag and drop into applications. And so the library takes care of finding the locally installed Shatter client and saying, hey, instead of just doing a DSA signature, ask the Shatter client for a DSA signature and give me the result back when you're done. So here's what the Shatter client looks like running on Android. Like I say, it just manages the device for you. That's where you do enrollment of new devices, revoking, initialization. If you have it set up for notifications, then whenever a request for doing an operation is received, it pops up. You can, of course, set this to automatically accept or reject. And an interesting thing that you can see from the screenshot is you've got a log of requests, which doesn't seem that phenomenal at first, until you think about what happens when one of your devices gets stolen. So if an attacker steals one of your devices, only one, not the threshold number, and all of your devices automatically participate, they can use that device to do a bunch of things, like they can sign a whole bunch of emails. But because of this strong theft resistance property, even though they get a bunch of signed emails, one, they can't sign more after you notice that they've stolen it, and two, you're guaranteed to get an audit log on your other devices, anyone that they've contacted in order to participate. And so even though your device has been stolen and the attacker has done some damaging things with it, you can go back and see exactly what they did and when. Some of you might have played with Intel Edisons. This picture is mostly just for fun. You can see I've got some Canadian coins there for scale. We put elk and beavers on our coins. So Intel Edisons are these meant to be just little chips for making Internet of Things applications, devices. It's very tiny. They're like $40, and they just run an entire Linux distribution. So all I had to do to get this working was log into it, install Java, and I could run the Shatter client. Then I wrote just a small, tiny little wrapper to drive the screen and the buttons. This is the Android Wear version of it. It only does these accept, reject things. And this particular smartwatch is a Moto 360. An interesting thing about the Moto 360 is it has its own built-in Wi-Fi. So to connect to the internet on it, you don't need to proxy through a smartphone. Interesting things happen to the threat model when you're proxying your connection through another one of your devices. They're not really two separate devices in that case. So to talk a little bit about the algorithms, I won't go into detail other than to say that DSA is digital signature algorithm, and there's an elliptic curve version of it. The threshold version of this algorithm is extremely new. Someone just came up with it last year. It wasn't me, it was Gennaro. Rosario Gennaro is a very famous cryptographer. They came up with it last year. They came up with it for some Bitcoin stuff that I don't care about, but I was able to just use their algorithm anyway because it's a threshold version of DSA. And so if you have any application that uses DSA signatures for authentication, for example, anything that implements off-the-record messaging, OTR, which is the protocol that Signal is based on, can then just have its DSA call replaced with a threshold version of DSA. So we picked an OTR client. In particular, we chose ChatSecure, which is an Android client that supports OTR and uses DSA signatures. ChatSecure is by the Guardian Project, and someone from the Guardian Project is here. I saw that on the program. Hi. I'm going to yell at you later because the Guardian Project discontinued the Android version of ChatSecure. But we still have it. Yeah, so you can either see me later or run from me, whichever you like. Yeah, I know. Like I said, the Signal protocol, which is also used in WhatsApp, Google Allo, Facebook Secure Chats, is kind of catching on as the de facto end-to-end encryption standard for instant messaging. They all use the Signal protocol, and Signal gets its authentication not from DSA, but this thing they call triple Diffie-Hellman. So we do actually have a threshold version of that as well. It's extremely simple. I could show you it on a whiteboard in a minute if you wanted. It's extremely fast too, which is nice, but it didn't quite make it into the presentation or the talk. We came up with that a bit later. So here's what ChatSecure looks like, or looked like. This screenshot is incredibly boring, and that's exactly what we want. We want apps to be minimally changed and to be backwards compatible so that the user barely even notices the difference, other than the fact that they had to install the Shatter client and set it up. So you start, so you open up ChatSecure, you hit Start Encryption. ChatSecure, the app in the background, finds the Shatter client on your device, says, hey, please threshold whatever, a DSA signature for me. The app sends it back, and it continues doing the protocol as it would normally, and we get the little locks on our messages. And as we all know, locks mean that everything is secure. Another algorithm that we implemented was threshold PIA encryption. If any of you are cryptographers, you would know that this is a very weird choice of algorithm. The only reason we picked it is because it's a sub-algorithm in the threshold DSA stuff, so we had it implemented already. So I said, let's just show the flexibility of our library and allow people to encrypt arbitrary things using PIA. So in this case, we took OmniNotes, which is a popular note-taking application. You can just create new notes, write things in them, checklists, that kind of thing. And we say when you open a note, you go to load its contents. You have to decrypt it from disk first, and so decryption is a threshold operation. So when you try to do decryption, it does PIA decryption, and it says to your devices, hey, please help me decrypt this. A nice thing about using a public key crypto system for this is that encryption is not a threshold operation, and so we can just, when you say, okay, I'm done reading this note, save it and close it, we don't need to do the threshold things just for closing notes. Once again, extremely boring screenshots. Any particular note, you say encrypt, and it gets a little lock icon. Everything is secure. And like I said, boring screenshots are what we're really going for with this project. Because this is an academic project, the only way we can get things published is if we evaluate them somehow. So we did that. We tested things with t equals 3 desktops, 3 smartphones, and then smartwatch, smartphone, desktop. And we said, first of all, how long does a signature take? How long does a decryption take? Decryption is pretty quick. 2.5 seconds is still a hang in the UI, but users are used to their phones being crappy anyway. Signatures, however, are quite long. 13 seconds is a huge amount of time. I would say, first of all, users are used to internet operations like sending an email, spinning for a little bit, so that's not too bad a deal. And also, we can just switch off to doing this in the background. However, something that we noticed while implementing these particular algorithms is that they have a very expensive part of their operation called zero-knowledge proofs. And they're just this crypto thing that takes a long time to do, but doesn't need to be done immediately. The point of these zero-knowledge proofs is to tell you, did someone in this group of people that participated do something hinky? Like, they still participated, but did they kind of misbehave somehow? Did they set a parameter how they're not supposed to or something? So you still get your signature back, and you can make sure it's valid. But you also have to get these zero-knowledge proofs, generate them, and check them, which takes a long time. However, the only reason you need that, however, is for checking whether devices did something bad. And so if we defer the zero-knowledge proofs, like we check them later, and we decide, like, how are we going to handle that with the user, that's a difficult question. But if we can defer them somehow by pushing them off and notifying the user later, we can actually drop this down to about half a second for signatures and a quarter of a second for decryption, which is pretty much nothing. The bandwidth is basically nothing. The way these protocols work is the device that you're initiating from sends a bunch of requests out to all the other devices. They respond. You send another request. They respond. So you just have a few rounds of this. It's all done in parallel, so it's really quick and very low bandwidth. So to conclude my talk, Shatter protects people, single people that have multiple devices, helps them with key management, gives them theft resistance to a certain point, and etc. The big goal we had with this is enabling end-to-end cryptography like Signal, WhatsApp, whatever, across multiple devices. We already have an implementation of a few algorithms, and it's free and open source at that link. Please don't use it to protect your secrets. Thank you.
First, I want to say that I really like the idea. It's a great idea to do it this way. However, I'm not sure how does key revocation work, and could you change your key and re-encrypt your data?
Yeah, so the way revocation works is basically, so if your threshold is 3, so 3, if you use these, like a threshold signature scheme, you never regenerate the private key in memory. You have the option to actually recover the private key. The protocol is different, and so every device knows that they're participating in this operation, allowing you to regenerate the private key. And so as long as you have a threshold number of devices left, you just run the operation where you regenerate the private key, so the same original key that you use for encryption or whatever, and then you split it up into a new set of shares, with a different threshold number, excluding the device that you're revoking. So you just don't give that device a new share. And old versions of shares are not compatible with new versions of shares or anything. There are schemes with, for example, Shamir secret sharing, where you don't even need to restore the original private key. You can just change everyone's shares that you want to, but that's really difficult with the more complicated algorithms.
But the key still stays the same, no?
Yes, the key itself stays the same.
You just change the parts, but not the entire key.
Yeah, exactly. Yeah.
Okay, thank you.
Cheers.
Another thing I was was thinking about a lot of devices, especially iOS, have schemes that protect the key in hardware. So in order for this to work, you have to be able to extract the raw private key, right?
Yep.
So is there a way to make it work with hardware protected keys?
That is a great question, and it's something that I've been spending a lot of time on lately, actually. The answer is, so what we want to do is take the shares themselves and protect those using like the trusted execution environment or whatever, or like an HSM. So that even if the attacker compromises your device, they still don't even get your share, or it's very difficult for them to. What it comes down to is how convoluted your threshold algorithm is. So for example, I talked about this new version of threshold DSA. The reason it only came out last year and not 20 years ago is because that algorithm is a beast. Like, it's got a lot of zero-knowledge proofs, it's got commitment schemes, it's got homomorphic encryption in it, all using that private share. And so basically the operations that the trusted execution environment allow you to do won't allow you to do threshold DSA. The signal triple Diffie-Hellman algorithm, though, is extremely simple. It's really elegant. And I'm fairly certain that I can trick the TEE into doing the math that I need for that. I haven't actually finished it yet, though, so it's probably possible. Yeah.
Just another thing, it seems that downloads are not working.
Thank you.
Thanks for your talk. You said that all devices need to be online and connected at the moment. Or do you have any hope that this feature, only one active device, will be or can be implemented at all?
Yeah, so as long as with your one device, if your application is internet enabled, or as long as you're internet connected at the time, you can do this cloud trick where you say, hey, Amazon Cloud is one of my devices. Some people have told me about this Amazon Lambda thing, which seems really promising for implementing it. And so if you're doing something like sending secure email with a private key, to send email, you have to be connected to the internet anyway. Like, when you're not connected, you just can't send instant messages. You can't send emails. And so that's okay. That's a perfectly valid restriction to say, hey, you need to be connected to the internet at the time in order to do these things, because you are anyway. If you're using something like your Notes application or encrypted file storage, it's not such a fair assumption then, because like if the person is traveling, they want to access their files, but they don't have an internet connection, then it really doesn't work. You can also do this thing where you have paper shares. Those are really only useful for recovering your private key, though. You could use them in an emergency for like sending an email or something, or decrypting things. When you're offline, but it's really not a good use case for those backup shares. So yeah, I think the best thing I've come up with so far for the single use case is using an always-on cloud service as one of your devices. Cheers.
I think we're just in time. Thank you for the presentation.
Thank you.
Hey.
Question?
Yeah.
Sorry. Yeah, one.
Sorry, last question.
Sure.
Thank you for your talk here. Was just wondering, what is the process if I just buy, for example, a new smartwatch, and I want to add it to...
Yeah, so you have a new device and you want to add it. Yeah, so that's actually the exact same thing as revocation.
Okay.
What you do is you just recover, you get a threshold number of devices together, you recover the original private key, and then you generate a new set of shares with n+1, and you hand them out to you, including your new device. And at the time, you also have the option, like if you're using a threshold of 2 before, maybe you want to increase it to 3 now, you get the opportunity at that time to do that. Changing the threshold as well at any time you can do. It's just another one of those enrollment revocation restorations. Thank you.